In this example, we will take the situation from the previous video and now include the force of static friction. The problem says, now let us imagine that there are no rollers on the crate and the coefficient of static friction between the crate and the floor is 0.485. The man still pulls with a force of 172 newtons, but this time the crate does not move. We are asked how much static friction force is resisting motion in this case. We're then asked what is the maximum possible static friction force the floor can exert to hold the crate still, expressed in terms of the force exerted on the rope. And then finally, what minimum force must he exert on the rope to move the crate? Well, the physical situation is very similar to what we encountered in the previous video. The three forces that were acting on the crate before are still acting on the crate now. So as we proceed to step 1 in the problem-solving process, draw a diagram showing all the forces acting on the object. These three forces are still here. The weight force acting downward, the normal force from the floor acting straight up, and the tension force in the rope acting at a 32-degree angle to the horizontal. The difference is, this time, we now have a friction force at work. So we now include the friction force on the diagram. Note the direction of the friction force is in this case to the left because the crate will be moving to the right. That means the friction force opposes motion. So now, with the inclusion of this new friction force, we have drawn a diagram showing all the forces acting on the object. Step 2 in the problem-solving process is to select a coordinate system, and we will remain with this coordinate system from the previous problem, with x being horizontal, positive to the right, and y being vertical, positive upward. The third step is to decide if any forces need to be broken up into components and to write out formulas for those components. The addition of the friction force doesn't really change the situation for step 3 because the friction force is purely horizontal. We still only have one force that needs to be broken up into components, and those formulas are the same. Please refer to the previous video for how we derived these formulas. Then step 4 is to use Newton's second law to figure out what the problem is asking you for. Well, the first thing we're asked for is the amount of static friction force that is opposing the crate's motion. The amount of tension force has not changed from the previous problem. The man is still pulling with a force of 172 newtons. Only this time, because of the friction force, because we now have a coefficient of static friction acting on the crate of 0.485, now the crate's not moving. We say, therefore, that now the acceleration in the x direction is going to be 0 because the crate is not moving. Looking at Newton's second law, remembering that Newton's second law is actually two equations, one for the sum of the forces in the x direction equals mass times acceleration in the x direction, and another equation saying the sum of the forces in the y direction equals mass times acceleration in the y direction. We can see here with our x equation that the acceleration in the x direction is 0. That means the forces in the x direction must be in equilibrium because the crate is not moving. We have two forces in the x direction. One, Tx, to the right, positive. The other, the friction force, to the left, negative. So when we go to add up those forces, we see that Tx is positive and the friction force is negative, and they must add up to 0. This can only be true if the friction force is equal to the x component of the tension. And so we can immediately figure out what the friction force is that is holding the crate still. That's going to be T times the cosine of 32 degrees. and that's a tension force of 172 newtons times the cosine of 32 degrees. That gives us a friction force of 145 newtons to 3 significant figures. Notice, this is the static friction force holding the crate still when we pull with a force of 172 newtons. The static friction force can actually be greater than this. As we increase our pull, the static friction force will also increase in order to keep the crate stationary. What we are asked for in the second part of the problem is to figure out the maximum possible static friction force that the floor can exert to hold the crate still. That is going to be the maximum static friction force is going to be the static friction coefficient times the normal force. So now we find ourselves in a situation that we typically are when trying to figure out friction forces, because usually to find the friction force, we must first find the normal force. We did not need to do that here because we have the information that the crate is stationary and we know the tension in the rope. But here, to find the maximum static friction, we must figure out what the normal force is. But that's easily done. We do the same thing as we did in the previous video, realizing that the acceleration in the y direction is going to be 0. That means the y forces are in balance as well. Because the crate is not moving left or right, up or down, both of these accelerations are 0. All of the forces are in equilibrium. As in the previous example, we have 1, 2, 3 forces in the y direction, 2 up and 1 down. The upward forces get positive signs. Normal force up, positive. The downward forces get negative signs. mg, down, negative, and ty, up, positive. And these all have to add up to 0 to keep the y forces in equilibrium. That then gives us the solution, which again we saw in the previous example, that the normal force is mg minus t sine 32. Now, we cannot figure out the size of this normal force because we don't know the tension force. We know it has to be more than 172 in the previous example if we want to move that crate, but we do not know what that tension force is. And so right now, the best that we can say is that the normal force is going to be 1,150, the weight force, minus 0.5299, that's the cosine of 32, sine of 32, times t. Taking this normal force and putting it in here, that tells us the maximum static friction force is the static friction coefficient, 0.485, times this normal force, 1,150 newtons, the weight, minus 0.5299, that's the sine of 32, times t. Solving this, we see that this comes out to be 526.7 minus 0.243 times t. I'm leaving an extra significant figure in there to help us avoid rounding error. So here's an expression for the maximum static friction force that the floor can exert. Notice how it depends on the tension, because the harder we pull, the more upward force we have. The more upward force we have, the less the normal force will be, and the less the normal force will be, the smaller the static friction force will be. because the tension force here is at an upward angle, the maximum static friction force depends on how hard we are pulling. Finally, we are asked, what minimum force must the man exert on the rope to move the crate? Well, once again, we take a look at the forces in the x direction. We see that those forces in the x direction are going to be the x component of the tension minus this static friction force. The box will move if that x component of the tension equals the maximum value for the static friction force. That maximum value for the static friction force represents the amount of horizontal force that will move the box. So Tx is T cosine 32, and we have seen here that the maximum static friction force is 526.7 minus 0.243 times T. We have to be very careful here, make sure that we don't make any algebra errors. The cosine of 32 is 0.848, so that goes on that side of the equation. We'll leave this side unchanged for now. But now we're going to take this, bring it over here, where it becomes positive. And so we get 0.848 plus 0.243 times T equals 526.7. This is 1.09 times T equals 526.7. And that gives us a tension of 483 newtons. So this represents the minimum amount of force that we have to exert so that the x component of that tension can overcome the static friction force and begin to move the box.